Welcome to qnawire.
For this question, we have our electron passing through an aperture and getting diffracted to a screen, right? A screen some distance 0.3 meters away, and as it passes through this slit, right, or this aperture, its uncertainty in its position, right, is confined to the size of this aperture. And this is by the uncertainty principle. This will affect the minimum uncertainty in the momentum in this particular direction, which we will call the y-axis. This is the y, this is the x-axis. So in the y-axis, the uncertainty in the position is fixed to be 0.5 millimeters, and this will affect the uncertainty in the momentum, right, which will be greater or equals to h power over 2 times 0.5 is 10 power minus 3. And if we were to calculate the momentum, we can actually calculate what is the uncertainty in the velocity, right, by dividing by m, right? So we take delta p divided by m, where m is the mass of the electron. So this is just 9.11 times 10 power minus 31. Should get an uncertainty of about 0.12 meters per second. Now to find the uncertainty in the position of the point when it strikes the screen, say we have an electron that is moving towards the screen. Now because of the uncertainty in the y direction, right, in the velocity in the y direction, right, in the worst case scenario, we have some electron that is moving up or down with a velocity of 0.12 meters per second. Right, this is the worst case scenario, where there's a spread, right, of velocity, right, in 0.12 meters per second, either up or down. And the further away it travels, the longer it will actually affect our distance when it reaches the screen, right? So let's say if it travels for a short distance, right, then the uncertainty in the point would just be equals to 0.12 meters per second multiplied by the time taken to travel this place, right? Then this will be the maximum uncertainty in the point before it reaches that place. So in the same idea, right, when we travel further towards the screen, there is this uncertainty in the velocity. So in the worst case scenario, if we have a particle that is traveling with an extra velocity downwards of 0.12, we want to find what is the position it will reach, right? This is the uncertainty in the position when you are at the screen. So delta r is equals to delta y times, delta v times the total time taken to actually move this distance. And we've got to assume that this distance is just approximately the same, right, as the 0.3 meters, right? there isn't very much difference when we are considering different angles. So this would be the approximate distance we're going to use. So the time taken would just be 0.3 meters divided by the speed at which it is traveling in the x direction. So the speed we can find by taking the kinetic energy divided by the mass. This is the velocity, because kinetic energy is half mv square. We can find the kinetic energy based on the acceleration of the tube. Right, the tube acceleration is 15 kilovolts, so this is gq times 15 kilovolts, where q is the charge of the electron, so this is equals to 15 keV. So what we have to do, we just substitute in. This is equals to the velocity in the y direction multiplied by the distance between them, 0.3 meters, divided by the square root of 2 times the kinetic energy, 15 keV, divided by the mass. Now in this case, of course, we have to convert the keV into joules, and we can do that by multiplying by 1.6 times 10 to the power minus 16 joules per keV. And we should get our delta R to be about 4.78 10 to the power of minus 10 meters. So this is the uncertainty. And well, will it affect the clarity of the picture? The answer would be no, right? Because it is very, very small, right? It is on the order of 10 to the power minus 10, right? Which is like approximately the size of an atom. Right? Because it's so small, the visual that or the picture that we see on the screen is not really affected by the uncertainty principle. Right? It's not, will not really affect the direction patterns that we see.